Hello everybody, I'm Rongxi and I'm here to talk about my FYP, Data Augmentation for Computer Vision Problems. Let's start with an overview of my project. So what are computer vision problems? Computer vision is about teaching computers to see and understand pictures and videos. So overfitting is actually a big issue where computers get really good at recognizing specific pictures that you have seen before, but then struggles to see a new one. So what exactly is data augmentation? Data augmentation is like making changes to pictures or data to help computers learn better. It's really useful when there's not a lot of data to work with, because it helps the computer to get better at understanding things without needing new pictures or data. Our research gap here is the ineffectiveness of traditional data augmentation in small datasets for significant model improvement. My research objective is to overcome current computer vision data augmentation limitations through GANs and diffusion model integration, combining traditional method with GANs and diffusion and enabling the generation of diverse, realistic synthetic data, and enhancing training and generalization of computer vision models. Before we start, let's go over the main ideas that we'll be using for the project's development. Let's start with the traditional data augmentation methods. We have the geometric augmentation such as flip, rotate, scaling. We also have color transformation. Here we see saturation being adjusted on our best image. Lastly, the mosaic augmentation, which is like different pictures and putting them together to make a new picture. This helps the computer learn from lots of different things at once. So previously we mentioned GANs, short for Generative Adversarial Networks, a synthetic image generation model. It works by pitting two neural networks against each other. One network, the generator, creates new data instances, while the other, the discriminator, evaluates them for authenticity. The generator creates fake data to try and fool the discriminator, while the discriminator aims to distinguish between the real and fake data. This competitive process continues until the generator produces data that is indistinguishable from the real data, resulting in the generation of high-quality synthetic data. We also mentioned a diffusion model. It's another type of synthetic image generation model. The diffusion model operates by gradually transforming a simple noise distribution into complex images through a series of diffusion steps. Each step involves applying a series of transformations to the initial noise, progressively refining it to generate more realistic image data. The process involves understanding the parameters of the diffusion process, which helps to understand how clean or noisy data are related at each step of the transformation. During inference or generation, the diffusion model starts with noisy data, with noisy images, and then use the learned transformation in reverse to get clean or realistic data samples. In our research, we'll be using diffusion GANs, an easy-to-use model that combines both GANs and diffusion, enabling creation of realistic datasets. We will use YOLO Wi-Fi for training our image detection model. Now let's talk about our research design. We will initially train models separately using each traditional augmentation method before combining them to train a unified model. We will train models using synthetic image from diffusion GANs and traditional augmentation methods. Training will involve 100 epochs with the YOLO V5S model. Using an unaugmented model as the benchmark, we will then assess the impact of synthetic images on the model effectiveness. Here is a sample of our dataset. Since data augmentation is effective in training model with smaller sample size, we will focus on augmenting the bear class, which represents one of the smallest group in the COCO dataset. For evaluation, we will utilize the MAP at 50, which stands for mean average precision, at an intersection over union threshold of 0.5. Now, let us move on to the results and analysis. Here is a quick look at how our results turn out. As you can see, training our model using original with 100% synthetic images while applying all traditional augmentation methods has the highest validation score as compared to other models here. We also ran some inference using two models found online to show how the models perform during test time. We can see the confidence score and area of bounding box in each inference. During testing with our model, which was trained with all augmentation methods, including DiffGANs, we observe a consistently high and stable confidence score, which aligns with the validation results. The effectiveness of computer vision models in object recognition relies on the diversity of training dataset. Models trained on limited dataset might face difficulties with varying perspectives. Enhancing performance requires a diverse dataset with different object views. So in conclusion, applying data augmentation and incorporating synthetic images notably enhances performance. That brings us to the end of our presentation. Thank you for your attention.